Hi, thanks for joining me. In this video, we're going to dive into the world of group theory. We'll talk about the known origins of abstract algebra and one of the reasons it was developed as its own branch of mathematics. I'll then introduce the formal definition of what a group is, and finally we'll get into some examples to help explain why group theory is important. We'll cover some theoretical and real-world examples that I found most helpful when I was starting. Group theory's beginnings have been attributed to many different branches of math. Some of these include, but are not limited to, advancements in linear algebra, the development of number theory, and studies contributed to geometry. The most compelling origin story that I know about is a group of mathematicians' attempts to define general formulas for finding closed-form solutions, also known as roots, of higher degree polynomials. For background, the root of a polynomial is where it crosses the x-axis when plotted. For a linear polynomial, there exists a single root. For a quadratic, there's 2, for a cubic, there's 3, and so on. There were attempts to find the general equations for fifth degree or quintic polynomials and higher, which was eventually proved to be impossible. For a more concrete explanation, let's throw back to the good old middle school days. To solve for the roots of a quadratic polynomial, there's first the general equation, which we then set equal to 0, to solve for the x-intercepts. Lastly, we'll solve for x to get both roots, which I'm assuming this equation is very familiar to many of you watching. One of the most important definitions for group theory is how to be able to identify if an object is a group. A group is a set or a collection of objects which can be denoted as G for now, with the binary operator, which will give it the arbitrary symbol of a star or an asterisk. This can be written as the ordered pair G, star. There are criteria to help define what properties of a binary operator must have for an object to be defined as a group. These specific restrictions are as follows. First of all, the binary operator must be associative. Notice right away that this excludes division and subtraction. We know from previous experience in math that neither of these operands are associative. The associative property looks like the following. Secondly, there must be an identity element, denoted E, within the set. That identity must be the identity of the binary operator. This can be seen as E binary operator G is equal to G binary operator E, which is equal to G, for all elements G in G, or all elements in the set G. Notice how this always shows that the identity must be commutative. Another identity that many of you might be familiar with is the identity matrix in linear algebra. That helped me at first, so if you do matrix multiplication, you multiply the identity against any other matrix, it'll give that matrix back. Lastly, for a set to be a group, a set must contain an inverse for every element in the set. This means that for all G in G, or for all elements in the set, there must exist an inverse of those elements within G, such that G times G inverse is equal to G inverse times G, which you'll notice again is commutative. All of that is then equal to E, the identity. An example of this for the two binary operators that we know of right away, that we know that contain inverses are, for example, 2 times 1/2 is equal to 1, where 1 is the identity for the binary operator of multiplication, 4 plus -4 is equal to 0, and 0 is the identity of a group with the binary operator of addition. So, just a reminder, all of these properties must be fulfilled in order for a set with a binary operator to be noted as a group. We'll start applying this definition of a group to some theoretical examples first. We want to see if the set of integers under the operation of addition is a group. First, referencing the rules of our binary operator must satisfy to be a group, we know that addition is associative, so that first rule can be checked off. Second, we know that the identity of addition is 0, and the set of integers contains 0, so that is also satisfied. Lastly, every integer in the set has its inverse in the set, since the set contains every integer's negated value. These three components are all being satisfied, so that means that the set of integers under this operation is a group. Note that the same goes for the rationals under addition, the reals under addition, and the set of complex numbers under addition. The next example asks the question of whether the set of rationals under the operation is a group. First, we know that multiplication is associative, so the first criteria is satisfied. Second, we know that 1 is the identity for multiplication, and 1 is contained within the set of rational numbers, so that can be checked off. However, we do not every element of the rational number set contains an inverse. Here, 0 does not contain an inverse because of the specific binary operation. Thus, the set of rationals under the operation of multiplication is not a group. The final example, very similar to the prior, with the exception that we're excluding 0, is the last one that we're going to look at, and you can probably deduce that this helps us clear all three criteria. 1, we know multiplication is still associative. 1 is the identity for multiplication and is still contained within the set. And now that we've removed 0 from the set, all of the elements in the set have an inverse, making the set under the binary operator a group. The last part of this intro to group theory is a real-world application. In our case, we'll be looking at a triangle. Before we move forward, notice the placement of the vertices. Where the vertices are positioned right now is representing the identity model of the triangle. Anything we do to this triangle will be compared to this identity. Don't worry, you won't have to memorize this. I'll have it on every single slide so we can compare with ease. In this exercise, we will be performing actions onto this triangle. This includes rotating and reflecting that triangle in positions that look like the identity. However, the vertices will be in different places. The goal of this exercise is we'd like to be able to describe a set of unique actions for an equilateral triangle. This group of symmetries above features the actions. This triangle is known as the dihedral group of 6 elements, or D6 for short. A dihedral group is a group of symmetries of a regular polygon, and the elements in this case represent the actions that can be implemented upon that polygon. Also notice that the symmetries of a given set, in this case D6, form a group under composition, which is going to be our binary operator. To remember what composition is, think back to algebra when you compose two functions together. Here's an example of that. So here's our identity triangle on the left. What kinds of actions can we take to maneuver this triangle where it is in a different state than the identity, but we can easily get back to the identity if we wanted to? The first one that comes to my mind is rotation. A single clockwise rotation results in the triangle looking very similar to the identity, but with the vertices in different positions. We can label this action with the letter R for rotation. What if we wanted to rotate twice? Let's start again with the base model and rotate once. Based off of that initial rotation, let's rotate one more time. It will have a different configuration of the identity than we originally had, but we are able to rotate it back 2 times or rotate it forward once, and we can get back to the identity with ease. We'll label this action R squared. I remember when I was first learning this action, it seemed more intuitive to me to initially want to put this as R times R or R plus R, because it seemed like these events were independent at first. But remember that second rotation is dependent on the result from the first rotation, meaning that we have to compose the two together. Also notice that I have R composes R with the labels first and second in seemingly backwards order. This again goes back to our previous knowledge of how composition works and how it is indicated in writing. The first action is always written last. Intuitively, you might want to just keep rotating the triangle. Let's try it. Rotate once, twice, and a third time. After you've rotated 3 times, however, you'll maybe notice that the third rotation results in the identity again. This is the first instance of displaying that actions on objects are finite. You can keep rotating forever, but 6 rotations on this triangle is the identity, or 4 rotations is just 1 rotation, or R. This R cubed is not a unique action, and it will not be accounted for in the identity in identifying unique actions for D6. So we figured out that the number of unique elements for rotations are finite. So let's find a completely new but not totally unrelated action. The next step is to implement reflections as actions. To start, let's consider how many unique symmetries that this object will allow. We can flip along the first vertex, the second, and the third. This identifies 3 unique actions. To stick with simple notation, we're going to only worry about rotating along the middle axis, where the first vertex is right, and you'll see why in a little bit. We've all practiced reflecting along axes in school at one point or another. Usually this is featured around an x or y axis, but here we're going to have this invisible line that runs directly through the center of our object. Completing this action of reflecting along this axis results in the following configuration. We'll label this action with an S for symmetry. The natural next guess that we can take for finding unique actions is to reflect along vertex 1 twice, similar to our idea of rotating twice with r squared. As you might be able to see in your head already, flipping twice results in going back to the identity. This results in not being able to identify this as a unique action. We've now identified a finite number of reflections that we can implement onto this object, so let's try to find the other unique actions. Now, going back to our original diagram with all the different dotted lines, the next question is, how are we going to be able to flip along vertex 2 if we're only supposed to reflect along the axis going down the middle? The answer to this is that we can combine different variations of rotations and reflections to create the desired action. For example, if we rotate our identity triangle clockwise one time and then reflect it along the center axis, we can see that this looks like we've reflected along vertex 2. Remember that these actions must be written in terms of composition, since the reflection depended on the initial rotation, or else it would not have been unique. To reflect along vertex 3, there are 2 different approaches that I found which gave the same result. The first being a reflection and then a rotation, as displayed here. And the second being 2 rotations and then a reflection. So, what is all of this for? Well, a quick reminder on what the definition of a group is. So in this case, our set is D6, the dihedral group, with 6 elements, and the binary operator is composition. To officially be able to write out what this group looks like, we can create set brackets and fill in all the known unique actions that can be put upon this polygon, the equilateral triangle. So the first usually written out for any group set is the identity E. This is always included in writing out the set of actions upon an object in a group. Then we can include the rotations, and finally the symmetries. So this is your first created real-world group. I hope this example was helpful in making this topic a little bit easier to digest. My references for this are Dummett and Foote's book on abstract algebra, as well as Visual Group Theory by Nathan Carter. I hope you enjoyed this video, and I hope you learned something from it. If you did, don't forget to give it a like for me and let me know that I should produce more of this type of content. The process of relearning and getting to review this stuff has been really enjoyable for me, and I'd love to cover more if you're all looking for more math here. I was planning on making a video explaining more math notation at some point in the future, so let me know down below if you think that'd be helpful or if you have any other suggestions. Thanks!